So let's just say Z is a standard normal random variable. Okay, so Z has the location parameter equal to 0 and standard deviation or scale parameter equal to 1. And X is defined as a function of the standard normal random variable, which is Z square. It says compute the probability density function of X. Okay, so we are going to apply 4 steps. Step 1, a standard normal random variable can theoretically take any value from -infinity to +infinity. However, if we take the square of the real values, then X can only take non-negative values, right? So the square of any real value can only be positive or 0. So X can take non-negative values. So we have determined the possible values that X can take on. Step 1. Step 2. We need to determine the CDF of Z. However, the CDF of standard normal random variable cannot be computed, but we know that it has the solution of that integral. Okay? It does not have any closed form, but it is denoted by phi Z, phi at Z. The third step, we need to determine the CDF of X. What is X? X is the square of Z, right? So the CDF of X at X, which means the probability of X to be less than or equal to X, is equal to the probability of Z squared to be less than or equal to X. So as we know, the definition of X is equal to Z squared. Now, the inequality stating that Z squared to be less than or equal to X can be solved by this interval, right? So if Z is between minus square root of X and plus square root of X, then Z squared is going to be less than or equal to X. So that probability here is equal to that probability in the solution, and the probability that a standard normal random variable to be between minus square root of X and plus square root of X is equal to the CDF at the upper bound, which is square root of X, minus the CDF at the lower bound, which is minus square root of X. The CDF at minus square root of X. Now, how do you compute the CDF of a standard normal random variable for a negative value? So if you remember, the CDF of a standard normal random variable at a negative value is equal to what? 1 minus the CDF of the standard normal random variable at the positive counterpart of it. Okay? So that value is equal to that value. And if you write it like that, you will see that this difference is equal to 2 capital phi at square root of X minus 1. So the CDF of X is equal to this function. So what is the PDF of X? The PDF of X is equal to the square root of that function. The first derivative of that function. So what is the first derivative of this function? The first derivative of 2 phi square root of X minus 1, according to the chain rule, is equal to 1 over square root of 2x. So, first we need to calculate the square root of the inside. The first derivative of the inside. And the first derivative of the inside, the square root of X is equal to what? 1 over 2 square root of X. But because we have a 2 here as well, 2's will cancel out and we will get 1 over square root of X. And the first derivative of the CDF is PDF at the square root of X, which is going to be expanded as 1 over square root of 2 pi X e to the power minus X over 2. Okay? So this is how we compute the PDF of the square of a standard normal random variable. Now, my friends, in literature, the square of a standard normal random variable is called a chi-squared random variable with degrees of freedom parameter equal to 1. Now, you are going to learn about this chi-squared random variable in statistics course, which is Math 216. You are going to learn about the chi-squared random variable. It has parameter which is called the degrees of freedom parameter. So in this case, if X is defined as the square of a standard normal random variable, then X is called a chi-squared random variable with degrees of freedom parameter equal to 1. Okay, so this is the end of this chapter, my friends. This is one of the shortest chapters. Please do your readings. Your readings are very short in this chapter as well.